on the test.
So obviously, if a function is greater than or equal to 0, which number are we on now? Properties. Is it 7? Is the next one 7? Thank you. If a function is positive on the closed interval a comma b, of course the integral or the area will be greater than or equal to 0. That's obvious. Number 8. Let's take a look at the following scenario. Let's say I have a number that is denoted by lowercase m. Let's say I have another number that is denoted by uppercase m. And let's say I have an interval, of course, a comma b. And I have a function that can do whatever, but between a and b is not, this is not the squeeze theorem, but between the interval between a and b, on the interval a comma b, I can write this. Outside of that interval, I don't care what happens. But on the interval a comma b, I can write that the function is between m and m. Well, you could possibly say bounded, but okay. So then common sense will tell us that this area is smaller than this area, which is smaller than this area. Right? So therefore, I would write the area from a to b dx, do not ever forget dx, the integral from a to b dx, the integral from a to b dx. Those areas must be in this relationship. Okay, and we have an example for this. Let's take a look. So we illustrate this with here's a problem. They are asking us the same thing, use properties, don't calculate anything. 2 less than or equal to the integral from -1 to 1 from this dx less than or equal to 2 the square root of 2. They're not asking us to calculate anything, they're only asking us to show that that is correct. So 57 on 384. 2 less than or equal to the integral from -1 to 1 from the square root of 1 plus x squared dx less than or equal to 2 the square root of 2. In these situations, where is our starting point? We had something similar, but we did not have 3 pieces. We only had 2 pieces. So where was our starting point? And what am I trying to do? As long as I determine, I have the function in between and I determine 2 numbers up and down, top and bottom, then everything else will follow. So that's what I'm trying to do. But I have to start somewhere. And where do I start? I have to start with what I know. And what do I know for sure? Go back to the notes from last time and you'll see where we started with the other problem. And tell me how to start. Very important. There's one thing we know. I don't know anything other than one particular thing at this point. For? Yes, so for x. That's all I know right now. That's all I know. That's carved in stone because it says the integral from -1 to 1, so that's where x is. And that is the only thing I know. I'm trying to, using this compound inequality, I'm trying to build the function in the middle. So knowing that the number is between -1 and 1, now I need to know where is x squared. So x is between -1 and 1. And what could x squared be? What is x squared between what and what? For x between -1 and 1, x squared will be between, for any number between -1 and 1, x squared will be between
0 and 1.
Right. Clear? Is that clear? So then x squared, not in general, but for any number between -1 and 1, when I square those numbers, x squared must be between 0 and 1. Would you agree? Yes? Okay, so then, for now, I built x squared. What will be my next step? After building or getting x squared in the middle, what should I do next? Yes, add 1 to all three sides. 1 less than or equal to x squared plus 1 less than or equal to 2. Excellent. So now I have built x squared plus 1 in the middle. But that's not good enough. Knowing that these three numbers are positive, 1 and x squared plus 1 and 2, I am allowed to apply what next? Right. In general, I'm not allowed to. But these are three numbers in sequence from left to right in ascending order. So now I can write 1 less than or equal to the square root of x squared plus 1 less than or equal to the square root of 2. And the whole thing is finished, right? Because the moment I have an upper number and a lower number and a function in between, what should I do now to all three sides? Yes, apply the integral. Very good. dx from -1 to 1, dx from -1 to 1, dx from -1 to 1. We can touch the middle. The middle is carved in stone, and that's what I wanted. But we can determine the sides, side integrals. So what would you say about the left one? Yes. You could say, since it's an even function, you can say twice x from 0 to 1. And Eddie will be very happy with that, right? So it's 2x from 0 to 1. Why? Because 1 is a horizontal line which is symmetric with respect to the y-axis, which is even. Okay, what about the other side? By the same rule, we have 2, the square root of x, I'm sorry, the square root of 2x from 0 to 1. And that makes it much easier to calculate or determine. So the left one, the bottom one is 2. The integral doesn't change, of course. The square root of x squared plus 1 dx, and the right-hand side is 2 the square root of 2. And that's exactly what they wanted us to show. The 2 is less than or equal to this, and less than or equal to 2 the square root of 2. So this is basically another way of giving us an estimate of the integral. It's not the best method, but we don't know how to determine the antiderivative of this, but we can say that it's between 2 and 2 the square root of 2 as the area. Questions? Questions?
Yeah.
Yes, please.
I know you just said it when I was writing. Could you tell me how we got to 2x? How to...
Yes, so one other option would be, which function prime is 1? And the answer is x. From -1 to 1. And that's how we get the 2.
Okay.
The same thing on the other side. Which function prime is 1? Because this is a constant goes in front. Which function prime is 1? So it's x. From -1 to 1.
Okay.
And we get the same thing. Or, since we know that this function that we determine the integral from is even, and the interval is symmetric, we can write twice the integral from 0 to 1 from dx,
Okay.
or 1 dx.
Okay.
Better?
Mm-hmm.
Perfect. Other questions?
Could you do one more?
Yes. Of course.
So you're basically trying to get to the answer. Right? Or, I mean, the question.
The idea for this problem is, if I show that the function is in the middle and I get a number here and a number here, that's the difficult part. Then I integrate this and I integrate this and I integrate this, and the sequence has the same inequality symbol.
Okay.
That was what I was trying to do.
Okay.
Because we do have the property that says m less than or equal to f of x less than or equal to the uppercase m of m. Then we apply the integral, and this area is smaller than this area and is smaller than this area.
Okay.
So that was the whole deal.
Okay.
But we had to start with x. That's all we knew. And then trying step by step to build this function in the middle. Once I have the function in the middle and some numbers left and right, I'm done.
Okay.
Because we apply the integral and get the area. Is that better?
Yeah, that's better.
Okay. Okay, so another one that we haven't looked at, we looked at these two. The other one that we haven't looked at is 58. So let's try 58. On 384. So this one says the square root of 2 pi over 24 less than or equal to the integral from pi over 6 to pi over 4 cosine x, of course dx, less than or equal to the square root of 3 pi over 24. Like before, I'm going to ask the same question. What is our starting point?
25, 6, and 5.
Right. So I know for sure that x is between pi over 6 and pi over 4. Okay. So what am I trying? What is my target? My target is to build what in the middle?
Thanks.
Careful. Cosine x. Very good. Now I have to be very careful. If function cosine if between pi over 6 and pi over 4 the function is increasing, then I will apply cosine and this to all three sides, and the signs will not change. But if the function cosine is decreasing between pi over 6 and pi over 4, then I have to reverse the inequality symbol. Is that clear? Let me say it again. So the inequality, the compound inequality looks like this. Do not ever write something like this or something like this, right? It's either this way or this way. Nothing else exists. Okay. So I have this pi over 6 x pi over 4. If cosine is increasing on that interval, cosine of pi over 6 will be less than cosine x will be less than cosine pi over 4. But if cosine is a decreasing function between pi over 6 and pi over 4, then the inequality symbol will reverse. This will be bigger, and this will be smaller. So we have to investigate that. So be very careful. Why didn't I have this discussion? Why didn't we discuss this here? Because the square root is an increasing function on positive numbers. That's why we didn't talk about it. But here, cosine, remember the graph of cosine is this. Looks like a vase starting at 0. So I have to figure out what happens here. It starts at 0 being 1, and it gets at pi over 2 to be 0. So between pi over 6 and pi over 4 is not an increasing function. So applying cosine to all three sides and not switching the inequality symbol, it will be wrong. So let's look at cosine. So here's the graph of cosine between 0 and pi over 2. That's all we care about. This is the graph of cosine. I'm not going to graph anything else. That's all I care about. Because this is 30 degrees, or pi over 6, and this is pi over 4. I cannot just simply apply a function and say, oh, that's it. So now applying cosine here, cosine in the middle, and cosine to the right, we'll switch the inequality symbols. Why? Because cosine pi over 6 is bigger. Cosine pi over 6 is bigger than cosine pi over 4. So the inequality will have to switch. So, therefore, if we remember cosine, so now I can write it in the correct order. The square root of 2 over 2 less than or equal to cosine x, less than or equal to cosine pi over 6 is the square root of 3 over 2. That's all we really needed. To be careful on, to determine the cosine in between and having that bounds, and what would be the next step then? What is the next step? What are we doing next? Yes, of course.
So the signs switch back.
No, I wrote them from here.
Oh, okay.
The square root of 2 less than cosine, because I don't want this incorrect. I mean, it's correct, but I prefer left for right, increasing, right. So I wrote this here, and I wrote this here, and I wrote this here.
Okay, gotcha.
So now we have the integral from pi over 6 to pi over 4 dx, the integral from pi over 6 to pi over 4 dx, the integral from pi over 6 to pi over 4 dx. The middle is what we wanted. And now we have to calculate left and right. They're not symmetric intervals. We have to calculate everything by hand. So this is the square root of 2 over 2, x from pi over 6 to pi over 4. And this one is the square root of 3 over 2 from pi, x, of course, from pi over 6 to pi over 4. So the left one will be the square root of 2 over 2 pi over 4 minus pi over 6, which is the square root of 2 over 2. The least common denominator is 12, so 3 minus 2, so it's 1. So the left piece is the square root of 2 pi over 24. And now the right piece, the square root of 3 over 2, still pi over 4 minus pi over 6, still the square root of 3 over 2 times pi over 12, and then the square root of 3 pi divided by 24. And going back, where is my first page? Right here. So this is indeed the square root of 3 pi over 24. And the other one is indeed the square root of 2 pi over 24. Thank you for asking that. It was a very interesting example. Very good. Any questions here? Is this clear? Okay. So now we are ready to go back to Fundamental Theorem of Calculus Part 1. Any questions again? Anyone? Any questions? Eddie, is this better? Anyone? Okay. So FTC Part 1. Fundamental Theorem of Calculus. Part 1. What was Part 2 telling us? Part 2 was telling us or showing us how to do what?
Find the area of the curve.
Right. In other words, how to evaluate a definite integral. Perfect. This one will tell us that it shows that differentiation and integration are operations. So part 1, and I'm missing a word and I'm waiting for you to come up with it. So Fundamental Theorem of Calculus Part 1, it shows us that differentiation and integration are
Inverse.
Thank you. Inverse operations. They are inverses of each other, which means if I have a derivative and I integrate it, I get the function. if I have an integral and I differentiate the integral, I get the function. Okay? So let's illustrate this. Let's take a look at the following scenario. I have a function. I have obviously an interval, a comma b. I'm going to call this f of t. Sorry. Any other variable but t, but x. For now, you'll see in a moment why. Doesn't matter really, but. So can anyone identify the area for us? How will I determine the area under the graph of f of x between a and b?
Integral from B to A. Right.
Yeah, f of x dx, from a to b, from f of x dx. Okay, very good. So, of course, it's t, f of t dt. Here's what I would like to do next. I'm going to say that x is a number between a and b. It can be here. 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 So this can be x, anywhere between a and b. And I would like you to think for a moment and tell me what this is. Before you say anything, let me give you a hint. There is a process or a procedure, and you'll tell me what it is. I don't want to name it. For which, let's say for x equals 1, perform some calculations and you give me 5. And then I'll say use 3 now, and you perform calculations and you give me 10. And then I'll say use -5 now, and then you perform calculations and you give me -100. So when x is a, obviously this is 0. When x is here, it's this piece. When x is here, it's that piece. When x is here, is this piece. When x is here, is the whole piece. What am I creating here?
A function.
Of course. Thank you. This is a function. And it's a function that depends on x. And this is a function given in a form of an integral. Function given as an integral. But it is a function. Why? Because we want to illustrate what we just said. What we want to illustrate? We want to illustrate the differentiation and integration of inverse operations. That's what we are trying to do. And that's what part 1 says. Every time we're given an integral like this could be x, or it could be tangent x, or it could be sine x tangent x, or it could be natural log x, or it could be x cubed minus 5. It doesn't matter. We're not asked to evaluate this. We will always be asked to find the derivative of this. This is a function. We're asked to find its derivative. Okay? The function is g of x, so we are asked to find g prime. In no other case like this, no case like this, we would be asked to evaluate. We can't. It's a function, unless you give me x. If you say evaluate this when x is 5, I'll perform the calculations and give you a number. But most of the time, we would be asked to find g prime, which means we are going to differentiate both sides to find g prime. Okay. Here's another question. Before you look at examples and before I didn't give you the result yet. What if I have in there a function instead of x, like tangent x? When I differentiate both sides, what should I get on the other side? Whatever, but times tangent prime, because that's the inner function. But if it's x, x prime is just 1. So keep that in mind. We're going to have plenty of examples. So we're asked here to differentiate g of x. Find the derivative of g of x. So we will differentiate both sides. What do you think we get on the right-hand side? Just a wild guess. It's okay if you're wrong. I've been wrong for a long time. in many situations. Yes, Andre? You want to say something? You don't have to.
F prime of X. Or well,
So
just the
careful.
function. The inner
Exactly.
function of X.
Exactly.
Okay.
So it is f of x. So let me write it one more time for you. So the function is given in a form of an integral. And we're asked to differentiate both sides. And we get g prime of x equals f of x. That's the fundamental theorem of calculus part 1. Now notice one thing. This has no effect. It can be anything except a function or x. It can be any number. But if it's not a number, you cannot apply the fundamental theorem of calculus part 1. This is required to be a number. This can be anything, x or any function you want. But this has to be a number. The lower limit has to be a number. So let's look at a few examples and then I'm sure you'll understand what's happening here. These problems are on page 394. So let's start with, let's say 10. 394. So g of r, okay, fine. From 0 to r, from the square root of x squared plus 4 dx. Use part 1 of the fundamental theorem of calculus to find the derivative of the given function. And the function is given in the form of the integral, because we're practicing fundamental theorem of calculus part 1. So I'm going to differentiate both sides, not before I make sure that this is a number, and this can be anything. It happens that it's just a variable, like we had it in the fundamental theorem of calculus. Good. So then, what do you think we're going to write? G prime of r equals? Excellent. Plus 4. I should write, I just want to, careful, no, there is no need, it's the derivative. Is a derivative. I should write times r prime. How come I don't? Because it's, right? It's 1. It's the independent variable. In this case, it's r, so r prime is 1. But what if I had over there r squared? Of course, I would have plugged in r squared, but what should I have had here then, if that was r squared?
2r.
2r. 2r. Very good. This is it. We were only asked to differentiate this function that is given in the form of an integral. That's all we were asked to do, and this is it. Ready for the next one? What about 18? Same page. Y equals the integral from sine x to 1 from the square root of 1 plus t squared dt. What is the first thing we have to look at here? And say, wait a minute. Of course, it's the same question, we're asked to find y prime. But here I have to say, wait a minute. It's not ready. Eric?
The bottom.
It's
limit
not a
would be-
constant. The lower limit is not a constant. So, but I know there is a property. But what happens then? Right. Y equals negative the integral from 1 to sine x the square of 1 plus t squared dt. Now it's ready. Now I can differentiate the left and differentiate the right. So 2 things here. Number 1, we're practicing the fact that when we differentiate an integral, we get a function. And number 2, we're looking basically at functions given in a form of an integral. And then we'll look at a numerical example. Okay, so then what will you write?
Negative square root of 1 plus the sine squared.
which is,
Cosine.
that's it. See the difference from the previous case? In the previous case, R1, R prime or X prime were 1, but sine prime is not 1. This is the inner function. When we differentiate and we replace t by the inner function, we have to differentiate that inner function as well by the chain rule. Okay, let's look at the next level. 58.
Quick question.
Yes, please.
So why don't you look at the lower limit of 1?
The lower limit can be anything. We're differentiating. So when you plug that in, you're going to get a constant. So when you differentiate, that will go away. So that's why this doesn't matter. If it's 1 or 100 or a billion, it doesn't matter. When you differentiate, it will be 0. Any number. Very good question. Thank you. Okay, 58. This function is denoted by uppercase f of x. It goes from the square root of x to 2x from arc tangent t dt. So then, this is no way ready for differentiation for several reasons. Number one, it does not have 1 here, right? Number two, I cannot have functions, both the lower limit and the upper limit. But the definite integral has a property. The integral from 1 to 5 is the integral from 1 to 2 plus the integral from 2 to 5. So I need to split this integral. The question is where? It doesn't matter. So I'm going to write this. You put in any number you want. It doesn't matter. Some of my students prefer 0, put 0. Others 110, put 10. It doesn't matter. So I split the integral between the square root of x and 2x into 2 pieces. From the square root of x to blah, and from blah to 2x. So it's almost ready, but not quite. Exactly. I have to flip this one. And then it's ready. So then we write negative the integral from whatever to the square root of x, arc tangent x dt dt, tangent t dt, plus the integral from whatever to 2x, arc tangent t dt. Now we can differentiate. We will differentiate the beginning, and we will differentiate the end. So can anyone give us f prime? So this one is a function given as a sum of 2 integrals. Okay, so I'm ready when you are.
Negative 1 and the square root of x times negative 1 of the square root of x.
Right, there is no negative. It's just the square root of x prime, which is 1 over 2 the square root of x. Is that okay? Very good. Plus
Arc tan 2x times 2.
yes, you can rearrange it a little bit. You can put 1 over 2 the square root of x in front and 2 in front, but that's fine. But just make sure that this is this, right? So make sure that you're not multiplying these or trying to simplify or anything. So arctangent is by itself. So maybe I should just rewrite it just to make sure. 2 the square root of x, arctangent the square root of x plus 2 arctangent 2x. Do not try to multiply the argument by something that is completely outside of the function. Okay. Do you think we should choose another problem? Huh?
how do you like, I don't know how to ask this, but like what is the reason for getting this? Like how do I can't really visualize
Yes.
it on a graph.
Yes, so you mean what are we trying to do with this?
Yeah, like why do we have to convert it into
We just want to show that differentiation and integration are inverse operations. So we're looking at a function that has an integral in it. And by differentiating it, we show that the derivative of an integral is the function. Or the integral of a derivative of a derivative is the function.
So if we have like an area, you can find the function with getting the derivative of the area.
Excellent.
Okay.
Yes. Exactly. If you integrate the area, you'll find the function. If you have the, let's say, the distance, and you don't have it, but you have the derivative, which is the area, you have the integral, which is, you don't have the distance, you have the velocity. You have the graph of the velocity, and you integrate that, you will get the distance. Because the integral of the velocity is the distance. You're integrating the derivative, so you get the function. Better? Good. Oh, we were going to look at an example, but I just wanted to ask you if you need another example like this. Yes? Yes. Very good. Would you like to choose? Please choose. These are between 55 and 59. And we looked at 58.
Can we do 57?
57 it is. Uh, 57, we have f of x is the integral from x. I think it's x squared, yes. So e raised to t squared dt. Again, this function cannot be differentiated just yet because in this form, we cannot use the fundamental theorem of calculus part 1. We have to work on this interval x to x squared, and only then, when we are completely done and they are in the appropriate setting, then we can differentiate. So what would be our first step then here?
Split it.
Yes, whatever. Then we have one more step. What is the step? Because it's required that the lower limit, I do the same thing, whatever that is, but it has to be the same thing. Negative, yes. From that number to x, e to t squared dt, plus the integral from e to t squared dt. Very good. And now we can find the derivative of this function given in the form of the sum of two integrals. So what are we going to write?
It's just a negative t, or negative e t squared. Alright,
Yes? We are replacing x, t by x.
okay.
Plus, I should write times x prime, but x prime is 1. And e raised to,
Same thing.
but it's squared now. And I have to square it. Yes. X to the 4th times 2x. Okay. So I was going to do this anyway, but Han asked. He's way ahead of me. I love it. Okay. Is it clear? Because I have to hold the book now, because otherwise it's gonna. Is it clear? Or is it blurry?
It's fine.
Okay. So we're given g of x, which is the integral from 0 to x from f of t dt. So obviously g of x is a function. It's a function of x, and it's given as a form in a form of an integral, where f is the function whose graph is shown. So here's the graph. and this is the integral from 0 to x, obviously is the area between 0 and any value here. Oops. Okay. So we're asked to evaluate g of x for 0, 1, 2, 3, 4, 5, and 6. Okay. If you'd like to write those for me, because I have to hold the book and I also have to show you on the graph. Ready? So f of 0 will be the integral from 0 to 0. So the integral from 0 to 0, how much will that be? 0. So g of 0 is 0. Please write it down. Oh, I'm so sorry. I'm sorry. 2 on page 394. 2 on page 394. I would have put it in, but you're right. I should have started with that. Sorry about that. Okay, so then g of 0 is 0, right? How much is g of 1? Half a square. Half a square of 1 by 1 is 1/2. How much is g of 2? Oops. So g of 2 is this area plus this area, but they are equal and opposites. So how much is g of 2? 0. It's 1/2 minus 1/2, which is 0. How much is g of 3? These are 0, don't even calculate them, so g of 3 will be? Excellent. Thank you. Negative, so g of 3 will be negative 1/2. Now g of 4. Yes, these two cancel out, these two cancel out, so g of 4 is 0 again. Han, is this clear? Yes, this was exactly your question. Thank you for asking. G of 5. These two annul themselves, these two annul themselves, and here I have 1 plus 1/2. So 3.5. So g of 5 is 3.5. G of 6, which means the integral from 0 to 6 from f of t dt. These are 0, these are 0, 1, 1, 1, 3. 1, 2, 3, I'm sorry, 1, 2, 3, 4. So g of 6 is 4. Yes?
How was g of 5 3.5?
So these two are the same, these two are the same. This is g of 5. No, g of 5 is 1.5, 3 halves. G of 5 is 3 halves, but g of 6 is 1, 2, 3, 4. Is that clear?
Yeah.
Correct me if I'm wrong anytime. Okay, finally they're asking us to estimate, of course, because this is impossible for me to tell you what this is. I have no idea. So if this is 3 by 1, this is more than half, right? So this is 3 by 1, but this area, I have to add the whole thing, right? We got to 4, right? Yeah, I have to add to 4, I had to add these p's. That's what they're asking us to estimate. So this will be half of it, but it's more than that. But by how much? Another 20%, another 25%, what would you estimate? So 3 times 1 so it will be 3 minus what? Minus 30% of 3? I'm going to say 3 minus 0.9. So my estimation is 2.1 just for this. So we came to 4, right? So 4 plus 2, this will be 6.1. So my estimate for g of 7 is 6.1. Am I correct? I have no idea. That was my estimate. Where does g have a maximum value?
6?
At 7, right?
Oh, okay.
6.1. Where does g have a minimum value? Look at your numbers. I don't have your numbers. It was negative 1/2 or something, right? It was at a 3. So at 3 it has a minimum value, and at 7 it has a maximum value. How will I sketch, of course, a rough graph? It cannot be an exact graph. How will I sketch this? If you give me those points, I'll sketch it. So let me also write them here so you have them. So this is 2 on page 394. So g of x was 0 to x from f of t dt. And we said I didn't mean that. Of course I didn't. X. So we had 0, 1, 2, 3, 4, 5, 6, and 7. And what did we get? 0 at 1 was 1/2. At 2 was 0, right? At 3 was negative 1/2. At 4 was 0. Okay. At 5 was, yes, 3/2, and then 4, and then 6.1. So now I'm asked to graph this, no problem. It will be a rough estimate of the graph, or a rough graph. So it goes to 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6, 7. 6.1. At 0 is 0. At 1 is 1/2. At 2 is 0. At 3 is negative 1/2. At 4 is 0. At 5 is 1.5. At 6 is 4. And this is the graph of g of x. A function given as a form, in the form of an integral. Any questions? Any questions? Any questions? Okay, my next step would like us to talk about indefinite integrals. So we have two types of integrals. One that we already know, definite integral. It has limits of integration. And it's a number. The problem is that I cannot check. I can only hope. The second type of integral is indefinite. The indefinite integral. Number one, I can check by differentiation. That's a bonus. Number two, it represents a function, comma, specifically the most general what? Thank you. And please remember it's a function. That's why I can check by differentiation. So how does it look? This is the indefinite integral. The integral from f of x dx, of course, we don't worry about whether it's continuous or not. Because we only determine the function. Good, so let's look at a few examples and practice this concept. And those problems come from page 404. Let's start with number 12. 404, the integral from x squared plus 1 plus 1 over x squared plus 1 dx. Which function prime is x squared? Plus, which function prime is 1? Plus, which function prime is 1 over x squared plus 1?
Right.
Very good. Plus a constant c. That's it.